Good day and welcome to our lesson. Today we're going to be looking at a very important aspect in chemical engineering known as combustion. Now, combustion is the burning of fuels to actually supply energy and to produce carbon dioxide and water vapor. If it's a hydrocarbon, basically, that's your general equation layout. So normally you've got a fuel that you burn in order to provide heat, energy, or steam, to heat up steam, especially in power stations. So it's very, very important that we understand how do we account for chemical reactions involving combustion problems. So now, first and foremost, let's look at the terminology around combustion. Now, as I've actually explained that when burning you must have fuel and then air normally you have oxygen that will actually give you the energy that you require, and the flue gases of course that emanate from that particular burning process. Now the other thing that's important is your fuel. So now your fuel can be actually different depending what kind of fuel you're actually utilizing. So you might find that you've got fuel like coal, you might have fuel like oil, natural gas, any other hydrocarbon that might be burned to actually produce that required energy. So it's very, very key that you actually understand the different kinds of fuels that are there. So normally the one that is used a lot in industry is coal. So now the other term that you need to familiarize yourself with is excess air. Now specifically this focuses on oxygen. Now what you'll understand about combustion problems is that air is always the excess reactant. So there's no need for you in combustion problems to actually determine which one is limiting and which one is in excess. What's in excess is always air, because air is easily withdrawn from the atmosphere into the combustion chamber, and the reactive component of air is oxygen that is actually needed for complete combustion. So more air than that needed for complete combustion. So that's the explanation of excess air. Now the other term is flue gas or wet gas. Now gases resulting from combustion process including water vapor. So all the gases that result in a combustion process, depending on what kind of fuel you're actually using. For example, let's say you're burning coke in the presence of oxygen, then you will have carbon dioxide and maybe carbon monoxide, and also you will have water vapor. So you include the water vapor, so that gives you the flue gas that actually leaves the chimney in a combustion chamber. And then the other one is offset analysis. Now offset analysis is the opposite of flue gas analysis. So offset analysis or dry bases. Now in this case, gases resulting from a combustion process excluding water vapor. So in this case, in your calculations in the material balance, you do not involve or you do not include water vapor. So you do the calculation on a dry basis, not on a wet basis. So the other term is complete combustion. Complete combustion is just simple as 100% conversion of the combustion reactant or of the fuel. Now, if the fuel burns to a maximum capacity, we call it complete combustion, or if it's complete conversion of that particular fuel. And then there's partial combustion or incomplete combustion. Now you find that a certain percentage, maybe 80% or 90%, that particular material is burnt to a certain percentage, not 100%, maybe 75%, maybe 80%. We call that incomplete combustion or incomplete conversion of that particular fuel. And normally you wouldn't really find practically 100% conversion. So partial combustion is normally close to the practical approximation. So now what's very important is actually air. It's pivotal in combustion. Now 21% of air is composed of oxygen and 79% is composed of nitrogen. So these are the basic assumptions that you should bear in mind when tackling combustion problems. And the average molecular weight of air is 29 kilograms per kilogram mole. Okay, so it's 29 kilograms. So if you've forgotten the average molecular weight of air, you can actually calculate it using 21% of oxygen and 79% of nitrogen, and also using their molar masses or molecular masses or molecular weight to actually determine that 29 kilograms per kilogram mole. So that's the average molecular weight that you can use. And the only reactive component of A is oxygen. So that's the basic assumption, because reaction of nitrogen might be there, but it's very limited amounts. So your nitrous oxides forming, you might not actually regard them. Even maybe the inert gases, you might not regard them. So here the general assumption is that the air is composed of oxygen and nitrogen, although we know that in real life we do have minute quantities of your nitrous oxide, sulfur dioxide, which you find that there might be in parts per million, because in parts per million, because they exist in very small amounts, and other lazy gases like argon are still there in the atmosphere, but we do not take them into account, so they are considered as negligible in combustion calculations. So the other last thing is that in combustion, oxygen is always in excess, and the fuel is the limiting reactant, something that I've just stated earlier on. So continued for air combustion. Now there's different kinds of oxygens that we need to actually gauge closer into. So you've got oxygen reacted is the oxygen consumed during the burning process. So that's the oxygen used up during the burning process. The actual oxygen that reacts during the burning process is called oxygen reacted. And then oxygen required. Oxygen required is the oxygen that is needed to burn the fuel completely if the reaction were to go to completion. So the oxygen required for complete combustion. So that's the difference between oxygen required and oxygen reacted. And then the oxygen unreacted is the oxygen that remains at the end of the process or the combustion process. So the oxygen that hasn't taken part in the reaction is called oxygen unreacted, or the unused oxygen, or the oxygen produced because now you actually account for it on the product side. So it's also important. Now there's also oxygen that comes in inherent with the air. It's called oxygen in fuel. This last oxygen is the oxygen in fuel. It comes inherent with the fuel, with the fuel. So it's the oxygen inherent with the fuel or that particular energy source. It doesn't come in with the airstream. It comes in already entrained in the fuel. Now the fuel, normally we will have your fossil fuels, okay, like coal and other hydrocarbons. Now what is key is that any hydrocarbon that you burn, you will produce on the product side carbon dioxide and water when it's burned to completion. However, if it's an incomplete combustion process, it will give you carbon monoxide, as stated by these examples. So this one is an incomplete reaction, and then this one is a complete reaction of a hydrocarbon. So we'll always get these products, carbon dioxide and water. If it's incomplete, you'll get carbon monoxide and water. Okay, remember that water is still a vapor. The fuel has a cost implication, and it's regarded as the limiting reactant in combustion processes. Now, fuel has a cost implication because we purchase or we buy fuel. However, the air we do not buy is drawn from the atmosphere, hence it's always in excess. Now moving forward, those are typical combustion reactions. So you can see this is an example of methane when it burns. Okay, this is what it produces when sulfur burns. You've got sulfur dioxide. When coke burns, carbon dioxide. If it burns incompletely, you will have carbon monoxide, of course. And then for hydrogen, it gives out water vapor as well when it burns in the presence of oxygen. And then the applicable equations. What's important is the percentage conversion. So percentage conversion is the moles of particular material that react over the moles of a particular material that is fed into the system. So you will get the percentage conversion of that particular raw material or that particular component of utmost importance. So the second equation here, it just signifies that there's 21% of air, 21% of air in the atmosphere. So you can get the moles of oxygen if you know the 21% of that particular air. 79% of air gives you the moles of nitrogen. Average molecular weight of air, this is how you calculate it. That's the formula. So as long as you've got the mole fractions and the molar masses, you can determine the average molecular weight of air. Likewise, now you can see the as excess. So excess air there, percentage excess is oxygen entering, subtract oxygen required to react with the limiting reactant, over oxygen required to react with the limiting reactant. Now this assumption is based on complete combustion. If the reaction were to go on to completion, this is the excess percentage you would have. So now you use this formula to calculate. Now this formula as well, marked in green, is also very key, because in order for you to find oxygen coming into the system, oxygen entering the system, is oxygen reacted plus oxygen unreacted. So the sum of the two will give you oxygen that initially came into the system. Oxygen required to react with the limiting reactant is given by this formula. So the limiting reactant fed multiplied by the coefficient of the excess reactant divided by the coefficient of the limiting reactant. Then you'll be able to actually determine the oxygen required to react with the limiting reactant if the reaction were to go to completion. Now another pivotal subject that is important here is elemental balance. Elemental balance is simple. Elements are neither created nor destroyed in a chemical reaction. They can only be rearranged. So if a chemical reaction takes place, you do not have a situation whereby those particular elements are destroyed. If you had nitrogen and hydrogen as reactants, you will still have nitrogen and hydrogen in the product. It's only that it's going to be formulated differently, or it's going to be rearranged differently. So in this case, you can see that there's nitrogen and hydrogen. This is the Haber process, and you can see there's also nitrogen and hydrogen on the product side. So nitrogen and hydrogen in this case have formed ammonia on the product side, but you still have the same elements: nitrogen hydrogen elements, nitrogen hydrogen elements. So elements in equals to elements out. Now this knowledge helps you to be able to calculate certain amounts in chemical reactions, okay, especially where it involves cold problems. It becomes an easier way of actually accounting for chemical reaction, especially in combustion problems. Okay, so we can use the number of elements to determine the amount of feed, side streams, and products in a chemical reaction unit. For combustion, we use fuel composition, air stream, water vapor, evaporation stream, refuse, and product gas streams. So basically, in a nutshell, this is what you need in order for you to actually understand and be able to tackle combustion problems. I'm going to leave it there for today. Thank you very much for watching, and you can go into the link below to be able to actually go and see how a tutorial of combustion is solved. I've actually solved it in detail. Thank you very much for watching. See you next time.